seminar style talks. Today's lecture is going to be on this paper by Witten. It's called Solutions of Four-Dimensional Field Theories by MJ. Okay, and the point of this paper of Witten is to try to understand the Seiberg-Witten solution and many, many generalizations thereof in simple pictorial geometrical terms, at least some part of it. Okay, so let's see. So what we're going to be doing is working in the context. You know, one of the really nice things about string theory is that within string theory, many facts about field theory become geometrized, and we're going to see one example of this working in today's lecture. Okay, so the context of the paper is type 2A theory in flat series. Okay, now, so I'm going to, I know not all of you know everything about, not all of you are very, very familiar with all aspects of string theory. That's okay, I'm just going to, tell you what we need for today's lecture. Okay, so type 2A theory is one of the 3 or 4 classic, or 5, okay, 3 or 4 classic 10-dimensional string theories. Okay, and let us recall, for instance, its field content. Okay, so type 2A theory, like every string theory, has the bosonic massless fields from the NS-NS sector, which are the metric, the dilaton, and the antisymmetric BB nu field. Every string theory has these because they come from the NS-NS sector, and the NS-NS sector is in every string theory. In addition, type 2A theory has the following objects. It has a gauge field. This is a Ramond in the RR sector. It has a gauge field, and it has a coupling to 0 branes. It has A mu nu alpha, which couple to 2 branes. And then there is the dual of this. I'm writing it, but it's not really there. It's the dual of this object. It's the 5 form. A alpha, beta, gamma, delta, epsilon. These two are dual gauge fields in the sense of the following. If I make the field strength of this is a 4-form field strength. And I make the field strength of this, that's a 6-form field strength. And if you demand that these two field strengths are Hodge duals of each other. Okay? So this is not an independent degree of freedom from here, but sometimes useful to think of it. The dualized field strength, dualized gauge field. Okay? Yeah.
This gauge field, does it come from two fermions combining to give a vector?
No, you see, it's a bit. You're talking about the vertex operator?
Yes, because from level matching condition, I know that we can have graviton.
Yes. It's in the Ramond sector.
So
it's in the Ramond
space-time fermion.
The Ramond spectrum. So how does that come about? The Ramond sector has spacetime fermions, but we're looking at the Ramond sector. So left would be spacetime fermions, right would be spacetime fermions. So it's the fact that when you take spinor times spinor, you get forms. Okay? And that's where this is coming from. Now, because the spinors have certain chiralities, you get either even forms or odd forms. It's different type 2a and type 2b theory, and in this case you get these odd forms. Okay? Yeah. Okay. So it comes from the zero mode of the fermion on the world sheet. Okay, or the spin field, it's another way of saying it. Right? Okay. Now, there is maybe just maybe just to convince ourselves we haven't forgotten anything, it's good to do some counting. Okay, so let's count the total number of degrees of freedom in all these fields. Okay, the total number of degrees of freedom, we're in 10 dimensions and we're massless fields. So the group theory relevant is SO8, it's SOD minus 2. So in the metric, it's -1. The -1 is the tracelessness. But then there's +1, that's 5, which was more or less the trace of the metric. Okay? And then the plus, there is 8 into 7 by 2. Okay? So this totally gives symmetric tensors, totally gives antisymmetric tensors. Together they give all tensors. So that's 8 into 8, which is 64 degrees of freedom. This is from the NS-NS sector. What about from the Ramond sector? Well, here you have 8, and here you have 8 into 9 into 10 divided by 2, by 6. Okay, so that's 2 and 4. So that's, I've done something wrong. Eight into 9. There you go. Thank you. There. Antisymmetric, yes. 8 into 7 into 6 divided by 6. Good. So that's 56. 56 plus 8 is 64. So 64 plus 64 gives the 128 degrees of freedom of bosonic degrees of freedom. There are also, of course, 128 fermionic degrees of freedom of type 2a theory.
You didn't count that because of the duality?
Yes, because that's not an independent degree of freedom. This, either this or this. Okay, but of course if you had counted it, you would get the same answer. Okay, just because a 5 form and a 3 form in SO8 have the same number of degrees of freedom. Because 8 choose 5 is the same as 8 choose 3. Okay, great. Now, there are 2-3 things that I wanted to tell you about before we start this our discussion of this paper. And the first thing I wanted to tell you about is the brains of these theories. All of these fields here, okay, all of these fields have supersymmetric BPS brains to which they couple. Okay, I mean not the metric, of course, but all of the form fields, B mu nu, A mu, and A mu nu alpha. B mu nu couples to the fundamental string. This you see from the fact that if you look at the world sheet action of the string, there is a term which is integral B. That's the coupling of B mu nu to the world volume of the string. Right? So B mu nu is the most familiar one because the states that are charged under B mu nu is the fundamental string itself. The fundamental string is the object that is charged under B mu nu. Okay? And the fundamental string is charged under a 2-form potential simply because it's possible to integrate a 2-form over the world volume of a two-dimensional sheet of a string. Just like a particle is charged under a one form, because it's possible to integrate a one form over the world line of the particle. Okay, all this you know. Good. But there are also these objects. There's a mu corresponding to which we have zero branes, d0 branes into A theory.
D0 branes are the lines?
D0 branes are particles, yeah. So they have a world line, they're just objects. Okay? Then there is this A mu nu alpha. Okay? There is this A mu nu alpha which couples to what are called two branes, two-dimensional objects. Neither zero branes nor two branes will play any particular role in what we're going to be talking about, except in the introductory parts. But there will be a key role played here by two other objects. Okay? This dual of A, this A with 5 indices, that couples one, two, three, four, five. That couples to D. That couples to D4 branes. Okay? Yes.
But it's not like these forms are integrated on the branes, but on the movement of branes.
On the world volume of the branes. Right? Just like for particles on the world line of the particle.
What is D?
What? D stands for Dirichlet. It's a technical term because the world sheet description of these branes is obtained by looking at open strings and putting fixed boundary conditions for the world sheet. Okay? So those of you who is only 2 or 3 people who've been through my string theory course know all about this, right? Okay? But it's just a technical term as far as we're concerned at the moment. Okay, excellent. And the last object that will also play a key role is the following. You know, just like we had the dual of A mu nu rho, A mu nu alpha, there is a dual of B mu nu. Now, the dual of B mu nu is a 6 form because B has a 3 form field strength, which is dual to a 7 form potential field strength, which comes from a 6 form potential. Okay? And that can be integrated over the world volume of another object. And that object is called the NS5 brane. Or the in his paper, Witten calls it the solitonic 5 brane.
And these things appear in excitation.
Okay. So, the first thing about these things is that they're solutions of supergravity. You take the low energy effective action of string theory, which is some supergravity, you can write down solitonic solutions, which are these things. Okay? Now, we understand the full string theoretic description of D-branes because of Polchinski's insight that the full CFT, including D-branes, is obtained by adding an open string sector into string theory, where the strings ending on the boundaries at the positions of the branes. The fundamental string, of course, was always there, which is what our basic excitation in string theory. The NS5 brane is more interesting. NS5 brane is more interesting. It is also, of course, a solitonic solution, just a solution of the supergravity equations of string theory. Okay, but there's a little more known about it. You know, there is the geometry that you see in string theory for an NS5 brane has a path that's far away and then a path that's near the brane. In the path that's near the brane, the solution becomes sort of quite simple. In fact, the solution becomes R6 times R phi, I'll tell you what that is, times SU2. Maybe I should call this an S3. S3K. What is this? R6 is R6. R5 is another R direction, but one in which the dilaton has a linear profile. Okay, so it's different from the other. In the other directions, the dilaton is constant, but in this direction, the dilaton has a linear profile. And the last three things is an S3, but the conformal field theory, the world sheet conformal field theory for which we understand completely, it's just SU2 Wechsler-Witten theory at level K, where K is the number of fibrils. Okay, and I'm not being very careful about K or K plus 2, depending on whether you're looking at the supersymmetric SU2, will be K or K plus 2, that kind of thing. Okay, I said this because even though we only understand this NS fibrine in all aspects in the supergravity regime, if you want near horizon geometry of this, the full world sheet conformal field theory for this theory is known. Because SU2, K we know, linear dilaton we know, and R6 we know. It's just the sum of these three. Okay, so what happens near the NS fibrine we know even when it's very stringy. Okay, last thing about these things that that you should keep in mind is their tensions. Okay, a fundamental string has a tension that is of order 1. That's what we see. It's just a simple probe. It's 1 over 4 pi. The action we wrote down for the fundamental string has a string tension. That's 1 over 4 pi alpha prime. No G string in it. Okay? Those of you who have were in my or some other string theory course know that a D brane always comes with a tension of order 1 over G. This is close string coupling. So 1 over G is, just the delta. 1 over G, the close string coupling. I'm not writing the factors of alpha prime. Those you can fix by dimensional analysis. If you've got a tension of a two-dimensional world sheet object with a world sheet that's two-dimensional, there'll be 1 over alpha prime. Three-dimensional, there'll be 1 over alpha prime to the 3 halves and so on. Right, just by dimensions. What's non-trivial is the string coupling, because that's dimensionless, it could be anything. And the tension of the NS fibrines goes like 1 over G squared. Okay?
Why is it NS?
NS is Nebu-Schwarz. It's Nebu-Schwarz because the name comes about because the field strength that supports this configuration. This object is charged under a field strength that is in the NS sector. In contrast to the D branes that are charged under field strengths that come from the Ramond sector. Okay? So, in particular, the zero brane has mass which goes like 1 over G. Okay. Now, end of the review of the BPS spectrum of extended objects in type 2A theory. Any questions about this? Now we're going to try to make a point and relate this to N theory, but first, any questions about it? Okay, all good? Excellent. Now, one.
So by this tension, you mean the coefficient that comes
outside the action? Yes. So the lowest term in the action of everything is the area of world volume.
So for particle, it's the mass.
It's the mass, exactly. Yes. So for instance, let's write it down. So if you've got a d-dimensional object, a d world sheet dimension, we will have Td times the integral area. Okay, for the particle that was length, and therefore Td was 1 over square root alpha. Here, depending on the dimension, you'll have different. Okay, that's in every world volume action. There may be more terms, but there's always an area term, and the coefficient of that is the tension. Okay, excellent. Now, I'm now going to tell you about another theory that will play a star role in this discussion. This thing that people sometimes call M theory. Okay? And you may think I'm skipping around a lot, but we will see in 2 minutes that I'm not. That there's a connection between these two things. Okay? So, as you remember from our discussion of supersymmetry, the highest dimension in which we could go and not have massless particles of spin greater than 2, and not necessarily have massless particles of spin greater than 2 was 11. Okay, you remember that. Okay, that in 11 dimensions we could get away with spins 2 or less. Okay, and in 11 dimensions the only way you will get away with spins 2 or less is by looking at the smallest multiplet. Okay, so there was a unique matter content with spin 2 or less in 11 dimensions. And this theory, the Earth theory, which we believe exists, which at low energies reduces to the supergravity governed by this massless multiplet, is called M theory. It's a very vague name. Sometimes people use the word M theory for all of string theory. Nowadays people talk much less about M theory than they did when I was your age. But okay. So there is this theory which reduces at low energies to 11-dimensional supergravity with a fixed Lagrangian fixed field content, fixed 2 derivative Lagrangian fixed field content. I'm going to tell you about that theory. That theory is a very beautiful theory. Its bosonic field content is very simple. It's got a metric and a 3-form. That's it. And then of course any dual, any Hodge star of the 3-form. Okay? Now let's do some counting for degrees of freedom. Remember, we're now in 11 dimensions. Okay, so this has 9 into 10 by 2 minus 1 degrees of freedom. Okay, and this has plus 11 into 10, no, in 9 into 8 into 7 by 6. Right, so that's 3 goes with 3 here and 2 goes with 4. Okay, and now let's check this. This was 44 plus 12 sevens 84, which is equal to 128. Okay, same number of degrees of freedom as we saw in type 2A theory. Now, the fact that the number of degrees of freedom is the same is not a coincidence. And one way of thinking of it is this way. Suppose we take this 11-dimensional... Oh, before we do that, what about the BPS objects, the supersymmetric objects in this theory? In this case, we know much less about them because we don't have world sheet string theory. Okay? But we can still do low energy effective supergravity. So we can look for solitons. People have discovered 2 kinds of BPS solitons in this theory. There's what's called the M2 brane and the M5 brane. M2 brane couples to this. M5 brane couples to the dual of this. Remember, this gives you a 4-form field strength. So it's due to a 7-form field strength, which is a 6-form potential, which can couple to the world volume of a 5 plus 1 dimensional object. Okay, so M theory here has 2 kinds of solitonic objects, M2 brane and M5 brane. Now, you could ask me, how does the tension of these objects scale with coupling? The answer to this question is the question makes no sense because there's no coupling in this. Okay, in string theory we had a coupling because the spectrum included a scalar, and the value of that scalar field at infinity was the string coupling. Here our spectrum includes no scalars, so there is no coupling. Okay? In fact, M theory is one of these theories with no dimensionless parameters. It's got a dimension full parameters, which you can think of as the 11-dimensional Planck scale. And then that's it. Okay? So the objects, the tensions of the M2 brane and the M5 brane in units of the Planck, are just set by LP to the appropriate power by dimensional analysis. Then there are some numbers. Those are interesting numbers, but we won't talk about them now. Okay? Excellent. So now you guys are experts in the low energy content and BPS spectrum of both 2A theory and M theory. Now, why am I talking about both these theories in the same breath? I'm talking about both these theories in the same breath for the following reason. Yes, that was 10D, this is 11D. Seems unrelated. Exactly. Now, suppose I take this 10-dimensional theory and put it on a circle. Louder. 11-dimensional theory and put it on one circle. Okay, then let's figure out what the field content will be. What is the field content? Well, first you have the field content that comes from metric on a circle. But metric on a circle could be G1111, where 11 is the circle direction. So that's a scalar. Let me use better notation. Let me call 11-dimensional indices capital. Okay. So Gmn goes to G1111, which I'm going to call phi. It goes to G11 mu, which I'm going to call A mu. And let me call this some A tilde. And then it goes to G mu nu, which is the metric. And what about this guy? A tilde mn, let's say P. We could have either one of its indices 11 or 0, 11. Can't have two because it's antisymmetric. Okay, so it could go to A mu nu rho or B mu nu. And if you look, you see that it's exactly the same field content. Okay, so the dimensional reduction of the field content of this 11-dimensional theory gives you the field content of type 2A theory. Already sort of interesting, right? Of course, everything's so tightly determined by supersymmetry that you might have thought this by itself is not very, very convincing. But now let's look at the let's look at the BPS spectrum. The BPS spectrum of this theory had a 5 brane, but the 5 brane could either wrap the circle or could not. Say it does not wrap the circle, it goes to a 5 brane. If it does wrap the circle, in the low energy 10-dimensional theory, it becomes a 4 brane. Goes around the circle. So only 4 dimensions left, 4 spatial dimensions. So it's a 4 brane. On the other hand, the 2 brane could either wrap and not wrap the circle or wrap the circle. If it does not, it becomes a 2 brane. If it wraps, it becomes a string. Now, I'm not going through the numerology, but okay. You see that this almost exactly matches the spectrum of BPS particles and BPS objects in type 2A theory. The M theory 5 brane with no wrapping is identified with the NS5 brane. NS5 brane of the M theory 5 brane wrapping one circle is identified with the D4 brane of 2A theory. The M theory 2 brane with no direction wrapped is identified with the D2 brane of string theory. And the M theory 2 brane with one circle wrapped is identified with the string of string theory. D0 is missing. What about D0? Now, you see, remember what is D0 charged under? D0 is charged under the gauge field A mu. A mu is the Kaluza-Klein gauge field. From 11 dimensions, we got it as the Kaluza-Klein gauge field. What is the charge under a Kaluza-Klein gauge field? Momentum in the 11th direction. So, D0 branes should be states with momentum in the 11th direction. Okay? And so, there are particles with momentum in the 11th dimension, and if you have n units of momentum, your mass is n by r. In low energy compared to the size of the circle, no charged particles, consistent with the fact that D0 branes are pretty heavy, which is 1 over G. Okay? And this identification of so the objects with momentum in this 11th direction are the 0 branes. Okay? This allows you to identify, by the way, that approximately speaking 1 over r of the 11th direction is 1 over G string times square root alpha prime, because the masses of the branes have to match. Okay? And by equating, I don't know, Newton's constants on the two sides, for instance. So, two relations that will allow you to, I'm getting no numbers right, just parameters. So, 1 by square root alpha prime G is equal to 1 by r. That's one relationship, and the second relationship is that the effective 10D Newton's constant should be the same. In string theory, the 10D Newton's constant is 1 by G string alpha prime to the power 4. But from M theory, this will be R by MP to the power 9. Using these two equations, we can rewrite G and alpha prime in terms of R and MP, or vice versa. So both theories are one-dimensional quantity, namely R times MP on the M theory side, and G string on the string theory side. Okay? And one-dimension full parameter, namely, let's say MP on the 11-dimensional side and alpha prime on the string theory side. And this is the proposed relationship between the quantities. Is this clear? It's coming from matching the effective low energy Newton's constants. You write down an effective action for the massless strings. The effective action in string theory is 1 over alpha prime to the 4 times 1 over G square. You remember this, right? 1 over alpha prime to the 4 had to be by dimensions. 1 over G squared was because metric comes from the NS sector. That's 1 over G squared that we see always. Okay? Whereas in M theory, in 11 dimension, it was just 1 over MP to the 9. But now there's this R, so you multiply by that R, do the integral over that R. Okay? And I'm doing all this, okay, because otherwise I would just be throwing things at you. In explaining this paper, I would just be throwing things at you and you wouldn't feel that you've got anything, because it's all in terms of things that are unfamiliar. So I want to make the objects that are going to appear in this paper a little bit familiar to you before we start using them, so that you feel that you understand. Okay, so we're going to take a little time to do this, but just let's worth it, because otherwise it won't be very convincing. Yes.
So when you said these D branes are like solitons of the low energy,
yes,
is this similar to the monopoles in some sense?
Very good. It's similar to monopoles, but with one strange thing. that had it been just like a normal monopole, it's actually an NS5 brane is much more similar to a monopole. Okay, and the reason that I'm saying this goes as follows: a monopole is an object whose gauge fields, when you write the action to the 1 over g squared, the gauge fields are such that field strengths are quantized in units of a unity. Therefore, the mass of a monopole is always of order 1 over g squared. Okay, and that matches the mass of an NS5 brane, the tension of an NS5. That's 1 over g squared. When we write the action such that we write a 1 over g squared outside everything, the field strengths of d branes are quantized in units of g, it turns out. Okay, and so these objects are lighter than ordinary classical monopoles. The mass is 1 over g rather than 1 over g squared. Other than that, very simple. Okay, they are like monopoles in the sense that they are solitons, but with a twist that is sort of somehow special to string theory. Okay, this is why you could write them as open strings in flat space. What is the connection there? You see, an object that has a tension 1 over g, when you multiply that tension with Newton's constant is g square. So it back reacts on space-time like g square by g, which is of order g. And therefore, which is small as g goes to 0, and therefore can be thought of as almost not having deformed flat space. Therefore, a d brane can be written as some small modification of flat space. Whereas an NS5 brane has tension of order 1 over g squared. Multiply by Newton's constant, you get g square. So the potential induced by this NS5 brane is order 1. It changes flat space at order 1. There's no way of writing it as an object in flat space. It's changing the... Right. So because d branes were lighter than NS5 branes, we could imagine a relatively simple description of them, and Polchinski found it. Okay? Okay. One last sanity check about this picture, and then we move to the paper. Okay. The sanity check about this picture goes as follows. If I've got everything right, then the tensions of d branes should also match across the two sides. Okay. Fine. Let's see. Let's first match the 5 brane tensions. Okay, 5 brane tensions should be mp to the power 6 on the M theory side, because there's nothing else for it to be. Has to be something mass to the power 6. Okay. On string theory side, we know what we're supposed to get. We're supposed to get 1 over the 5 brane, so that is 1 over g square, times alpha prime to the power 3. Okay. Now, is this correct or not? Okay, I'm just going to write down all the relations and then we'll check them. Okay. What about the mass of the tension of the 4 brane? This should be mp to the power 6 times r. Right? Because it's mp to the power 6 and then it's wrapping something radius r. This should map to 1 over g times alpha prime to the power 5, because this was a d4 brane on the string theory side. Okay. Already, okay, let's keep going and then we will see. Okay, then what about the mass of the 2 branes? The mass of the 2 branes here should be mp to the 3, because there's nothing else for it to be, and that has to map to a d2 brane, So this has to map to 1 over G times alpha prime to the 3 by 2. And the mass of a one brane, okay, which has to be mp square times r, should map to 1 over alpha prime. Because a string has tension 1 over alpha prime. Okay, so in order to check these, I hope they're correct. In order to check these, we will just use those two equations to compute R and MP in terms of G string and alpha prime. Okay, so let's do that. Let's see, so we can substitute from the first to get 1 over G squared alpha prime to the 4 is equal to square root alpha prime G by mp to the power 9, and therefore we get mp is equal to 1 by square root alpha prime wait, I've got the alpha primes and MPs mixed up. Sorry. This one should have been mass. Sorry. Right? It's mass to the 9th power is Newton's constant. Sorry, dimensions weren't working. Yeah. So this one was MP. And so we get MP is this times 1 over G cube, or 1 over G to the power 1 by 3. Right? Okay. And R. Now, R, we already have R from there. So R is equal to square root alpha prime G. So these two relations express MP and R in terms of alpha prime and G. Now we can use these to check that all of these work. Okay? Let's, except they don't look like they're working, right? What should have been 5 by 2?
The second one.
This one?
Yeah, right hand side.
5 by 2. Thank you. Okay. So let's see. Which one is matching? Sorry. This is matching with what? First two equations are matching. Last one is not matching. What have I done wrong? Just once. Okay, but let's look at what is matching and then we come to what's not. Okay, is this guy working? Yeah, powers of G are working. Alpha prime has to work. Okay, is this guy working?
Yeah, if it's 5 by 2, it's alpha. If it is 5 by 2.
Of course it's 5 by 2, right? Because dimensions.
Yeah.
Right, so let's see, yeah, so R has this extra G. Good. Is this guy working? Yes, that's working. Because 1 by G. So what have I done wrong here? Just 1 minute. P square. It's MP cube times R. That's what I've done wrong. So the tension of the two brane times R. Okay, and then that also works, right? Right? So you see that this is another check. Actually, I haven't shown you, but it works with numbers. Not only the parametric dependencies, but the numbers also work. So that's another check that this dimensional reduction is actually working out. But the thing that really convinced people was the following. If this guy is a dimensional reduction, then it makes a prediction for the zero brains. You see, we have gravitons with n units of momentum on the 11th dimensional circle, which are distinct states from n gravitons with 1 unit of momentum. Right? Now you take the circle, you could have n units, you've got a new field for that. It has the same energy, same value of all charges as n units of gravitons with 1 unit of momentum. All those are the same, but it's a distinct state. Now, this is a very unusual thing in physics, right? You've got this graviton, which is the distinct state from these other states, which carry more entropy. They're scattering states, because they can separate out. This is what's called a bound state at threshold. Okay? And one can argue on general grounds that in gravity, this thing is genuinely a distinct state. Okay? So, from the point of view of string theory, we see zero brains. What this is a prediction that the zero brain quantum mechanics, the effective world volume theory of zero brains, possesses a bound state, possesses one and exactly one bound state at threshold for every value of n, where n is the number of zero brains. Now you can understand that checking whether a bound state at threshold exists is a very delicate job, because it's got exactly as much energy as could decay to particles. Like usually bound states are below threshold, right? They've got binding energy. This is a bound state with no binding energy. Nonetheless, because these are supersymmetric bound states, people were able to use basically Witten index type ideas to convincingly demonstrate that this was the case. Okay, so this is a prediction from this picture for the quantum mechanics of zero brains, some one-dimensional quantum mechanics, 0 plus one-dimensional quantum mechanics, okay. Well-defined quantum mechanics, mathematically precise prediction verified. So this kind of thing happens all the time and convinces you that this picture is correct. Okay? So we now believe this picture very seriously. We take this picture very seriously. The serious thing is this, that if you want, notice that when this coupling becomes big in string theory, this radius here becomes large. Okay? In fact, what we can do is take R times MP from this. Is equal to, of course, alpha primes cancel, and we get G to the 2 by 3. So, G is a measure of how large the radius of the M theory circle is in units of M Planck. So you can ask, what happens to what does the effective description of type 2B theory become, type 2A theory become? Okay? When G is very large. And the answer to that, at least at low energies, it becomes 11-dimensional supergravity, where this new dimension being built up by the degrees, by the modes that come from zero brains and their towers. That gives you a new continuum. Okay, so this is this picture, that there is, we understand the strong coupling limit of string theory, of type 2A string theory. It's 11 dimensions where but recoupling the circle is tiny in 11 dimensions in the fundamental length scale. So it's a 10-dimensional. Strong coupling becomes an 11-dimensional theory. Okay, very different for type 2B theory. A strong coupling, type 2B theory becomes 2B theory at weak coupling. This S duality. But for 2A theory, strong coupling, it becomes this 11. Okay? How does it come about? It comes about because of the degrees of freedom in zero brains. You see, because at strong coupling, you have this 1 over G, the states which are at energies 1 over G, 2, I'm setting alpha prime to 1. 1 over G, 2 over G, 3 over G, and so on. Okay? That tower is the Kaluza-Klein tower of the 11th dimension, that 1, 2, 3, 4. And the fact that G is becoming small means that that circle size is becoming large. That's the origin of the new dimension. This descending of the solitons were a sign of the extra dimension. Okay? Is this clear? Okay. So, with all of this...
You're saying all the modes are becoming more and more continuous.
Exactly. It's become... The difference between them is becoming very small. Actually, something similar happens in 2. You know, what happens in 2B theory is that there are 2 strings. There are D strings and fundamental strings. Fundamental strings have energy, tension, 1 over...
D strings means strings which end on D strings?
No, D strings means 1 plus 1 dimensional ends of strings. D branes are places where ordinary fundamental strings can end. A D string is a 1 plus 1 dimensional manifold, one is time and the other is space, on which fundamental strings can end. That's the fundamental description of D branes. It's a manifold in space-time on which fundamental strings can end. We say D string because it's a 2-dimensional manifold. D2 brane, D1 brane. I haven't reviewed type 2B theory for you here. But type 2B theory has, instead of odd form potentials, has even form potentials. And so instead of odd, D odd branes, it has, instead of D even branes, it has D odd branes. So it has D string, D3 brane, the famous D3 brane of type 2B theory. Okay? So just the analog of this going to strong coupling went like this. The D string has tension 1 over alpha prime times GS. Okay? Whereas a fundamental string has tension 1 over alpha prime. Now, at weak coupling, the fundamental string therefore is much lighter than the D string. So the fundamental string is the fundamental object that moves around, whereas the D string is some heavy solitonic object. On the other hand, if you take G to infinity, roles are reversed. The D string is much lighter than the fundamental string, so that becomes the object that moves around. So in the S-dual description, the role of fundamental and D strings are flipped. You see, it's somewhat similar in the sense that what's happening is that G going to infinity is making something that was otherwise very heavy, making it very light. Right? This very light here was opening out in 11th dimension. There was interchanging the roles of solitons and fundamental strings. Is this clear? Okay? Excellent. One absolute last thing before we start real work. Okay? And that is this. On the world volume of D branes, when we go down to very low energies, if we've got a bunch of D branes, let's say coincident, and we go down to very low energies, then on the world volume of D branes, there is an effect at very low energies. There is an effective quantum field theory. Why is there an effective quantum field theory? There's an effective quantum field theory for a very simple reason. At very low energies, you don't have enough energy to excite any of the string oscillator states. Because we're going to energies that are small compared to both alpha prime and any other scale in the problem. You cannot excite the oscillator states. So the only states you can excite are the massless states of string theory. Now, there are massless states that are open strings and there are massless states that are closed strings. But the massless states that are closed strings are coupled to open strings via Newton's constant. And gravitational coupling is of the form that goes to 0 at low energy. G m1 m2 by r square. Those m's there. Telling you that low energies goes to 0. Right? Just dimensionally if you want. It's two derivative theory.
So when you say open strings are coupled to closed string by gravity, you mean graviton is in the closed?
Exactly. The closed string multiplet includes the graviton. Open string multiplet has, let's say, matter. So this is the coupling between matter and gravity, which functions via gravitational coupling. We know that gravitational coupling shut off at low energies. That's the fact that it's a two derivative theory. Right? Newton's constant has dimensions, so that effective coupling goes to 0 at low energies. This is clear, right? Okay? And therefore, if you go to very low energies, even though there are still closed strings floating around, they stop interacting with the open strings. Okay? So we've got these D branes, these are the endpoints of open strings. These open strings can maybe continue to interact with each other. But they stop interacting with the closed strings. There are no string oscillator states, so it's an interaction only of light matter degrees of freedom with each other. So it's a quantum field theory. Okay? And what Witten explained by understanding the structure of the interactions of open strings, easy calculation. Yes. You see, what we've got here are these open strings, and there are also closed strings. We're at very low energies compared to alpha prime and Planck scale. So there's no energy to produce string oscillator states. So these energies, the only states in our problem, are the open strings in the branes and the closed strings outside, the massless closed strings. Massless closed strings are gravitons and its superpartners. Interaction between gravity and matter is of the form that it becomes very weak at low energies.
There's no gravity coupling to gravity.
What? Gravity couples also to gravity, but also very weakly at low energies. And gravity becomes free at low energies, right? Stops coupling to everything else, stops coupling to itself. So at very low energies, the gravitons decouple from our description.
That's why it's a QFT.
That's why it's a QFT. We don't have enough energies to produce stringy oscillators, and we cannot the coupling to gravity shuts off. So it's just low energy open string states within themselves.
And oscillations perpendicular to the branes will be heavy?
Oscillations perpendicular to the branes are not heavy, but they are in the same multiplet. Oscillations of the brane, you are saying, right?
Yes.
They are in the same multiplet as the photon, as the gluon. So they are included in the light open string states. Okay, so they are included in the quantum field theory. Okay? So, for instance, if we had a D3 brane, okay, this is three brane in 9-dimensional space-time. So there are 6 perpendicular directions. So there should be 6 massless scalars. There should be a gauge field, and that is indeed the massless content of n equals 4 Yang-Mills theory. 6 scalars and a gauge field. And then there are fermions. Okay, so it's part of that multiplet. Okay? So the low energy theory on world volume of D branes is super Yang-Mills theory. It's actually always super Yang-Mills theory if you have infinite D branes in flat space. It's always super Yang-Mills theory with 16 supercharges, which may then be enhanced to superconformal charges. I'm not counting superconformal. The number of supersymmetries, Q type, not S type supersymmetries, is always 16. Okay?
You don't have gravity, that's right.
Why not 32, you're asking? You're asking why not 32?
Yeah.
It's because the presence of the brane breaks half of the symmetries. You see, flat space, in the absence of anything, preserves 32 supersymmetries. But a D brane is an object. It's a supersymmetric object. It preserves half of the supersymmetries, which means it breaks half of the supersymmetries. So in the background of a D brane, out of the 32 supercharges of the flat space string theory, 16 are broken and 16 are preserved. And in fact, the fermions on the world volume of the D brane can be thought of as the Goldsteinos coming from breaking of supersymmetry. From the 16 broken supercharges give us the 16 fermionic directions of the brane. That's one way of thinking of it. You can think of these, I suppose, these 6 scalars coming from broken translation invariants. Okay? Is this clear?
Also, no, I was
Go on.
asking just that if you have 32 supersymmetries, you will have this spin two fields, right? That's saying. Here we
Correct.
need your P and
Correct. It's connected. Because once you have this thing, you have only 16 supercharges, and that allows for a multiplet that preserves, that has spins up to 1 rather than 2. These are connected statements. Okay, 16, as you remember, is the largest number of supersymmetries you can have and still be a quantum field theory. And these are the theories that are on world volumes of brains. Okay, all good? Okay, excellent. Now, more precisely, if you are on a D brane, the world volume theory is UN in general, is UN Yang, if you have N brains together, you have UN Yang-Mills theory with 16 supercharges. Which Yang-Mills theory depends on which D brane. On a D2 brane, you'd have a 2 plus 1 dimensional UN Yang-Mills theory. On a D3 brane, you'd have a 3 plus 1 dimensional UN Yang-Mills theory. On a D4 brane, you'd have a 4 plus 1 dimensional UN Yang-Mills theory. That will be of most interest to us in this paper, the D4 brane. Okay? And the last question you might ask is, what is the value of the gauge coupling? What is the value of the gauge coupling? Now, you answer that question as follows. I told you what the tension was of these D branes. Okay? So suppose we are in a DP brane. So we will have G, then alpha prime to the power P by 2 plus 1. Plus half. P plus 1 by 2. If we are in a DP brane. Okay? And then you have integral, the thing that gives you area. So if you expand for small fluctuations, you get determinant, square root determinant of 1 plus del x delta alpha beta. Do you know what I'm doing? Right? I've chosen some directions of the brain as being, like this, and at lowest order, xm is alpha m. So I've just chosen my coordinates on the world volume of the brain to be p plus 1 dimensional coordinates in space-time, and the transverse fluctuations are parametrized in terms of those. I've written the square root, the area term out, and that's the square root term. But in this Born-Infeld kind of action, you actually also get a plus alpha prime fmn, f alpha beta.
This xm's of the fluctuation.
Xm's are the transverse fluctuations. But when you look at it from string theory, I can't remember if we discussed this in class. Probably, yeah, I remember. Remember we did it from looking at zero brane actions, boosting them and t-dualizing. In class we discussed this, that we got these FMNs in these actions. Now you take that and expand it to second order in F. Okay, ignoring this part. Determinant of 1 plus F becomes 1 plus trace F square. That gives you the Yang-Mills term. Okay? And that tells you, okay, and that tells you that the 1 over G squared Yang-Mills is equal to 1 over G times alpha prime to the power P plus 1 by 2 times 2 powers of alpha prime from here, so that's minus 4, right? Right, because the alpha prime came square. Okay, so that's P minus 3 by 2. Again, ignoring all numbers, this is the effective value of the Yang-Mills coupling on the world volume of a D brane. The effective value of the Yang-Mills coupling on the world volume of a D brane that you get out of string theory. This thing? Yeah. So let's do it in steps. So this was 1 over g times alpha prime to the power p plus 1 by 2 times alpha prime square times f square. When I did that determinant formula. Okay? Now I take the alpha prime square.
Thing alpha beta plus del x del x is like the induced metric pattern to this.
Exactly. Square root of induced metric.
So the action is actually metric plus alpha beta. You just wrote the metric.
I just written it in these particular coordinates. Exactly. So this was just h alpha beta. But the full Born-Feld action is h alpha beta plus alpha prime f alpha beta.
So is that coming from the fact that A nu T dual is the position of the
Yes. 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 Exactly. In fact, one way of seeing it is this. For a D0 braid, we know that the action must be square root of 1 minus v squared. 1 minus x dot squared. Okay? And then taking this and t-dualizing it. Okay? The velocity t-dualizes to field strength. Right? Because position t-dualizes to gauge field. Moving thing will be gauge field as a function of position, so t-dual. So one way of saying is that just the familiar fact that the action is square root of 1 minus v squared plus t-duality gives us this. Okay, excellent. So we get our final answer was that we got Yang-Mills coupling in terms of whose dependence on string parameters, we know. Okay, all of this would be much more work if I was keeping 2 pi's, okay. I remember I once wrote a paper on this paper we called NCOS theory, in which we tried to get these formulas right. It didn't make a difference, but just to show we tried to get these formulas right, including 2 pi's. Then Jeff Harvey wrote to us saying, something's wrong with your 2 pi's. So we looked at it, we corrected the 2 pi's, we put out a revised version. I'm really sorry, but something's still wrong with your 2 pi's. And he was totally right. Finally we got it. Okay, but it's a hard job to keep the 2 pi's straight. Okay, but parameters you see. We did it on the board without any notes. It's very easy. 2 pi's are much harder. Okay. Okay. Right. These kind of things here are useful to keep in mind because they're simple qualitative things. Getting numbers right, you look up Pulchinski. But this you should keep in your head. This mind map. Okay? Okay, excellent. So that's all I wanted to say about generalities. And we're not far from the end of today's lecture, so I won't go through the whole paper. What I will do is just set up the problem. Today in next class we can go through the paper. Okay. So what Witten wanted to do in this paper is to take this program that was so spectacularly successful with Seiberg of solving this program of solving n equals 2 theories and see if we could sort of see this in the context of string theory. The historical context is this. Around the same time that Ashok understood S-duality of n equals 4 theory, Seiberg did Seiberg duality, Seiberg-Witten did their thing. So also when string duality, 95, when Witten gave his famous talk in the strings meeting, explaining the M theory to a relationship. Okay. So these two things were happening in parallel. Both of them involved Witten in a crucial way. And then he began to realize that you could actually see one from from the other. That's the paper that it's not his most important paper, okay, but it's cool and it's fun, and it helps you see how things that looked so difficult, that we went 6-7 lectures through it, can actually be done in a few minutes if you think in the right way. Okay, fine. So that was these lectures meant to be a little bit in the spirit of fun, but you wouldn't be able to get the fun unless you had this background. That's why we went through it. Okay. Now, Witten's idea was the following. Witten's idea was, can I create, I know that I can put D branes together to get Yang-Mills theories with 16 supercharges. But Witten and Seiberg and Witten had already understood that this very interesting dynamics when you have theories with 8 supercharges. The theory we studied in so much detail over many lectures. Can we try to understand the dynamics of these theories with 8 supercharges from configurations of branes? That's the idea. Okay? So the context in which he made the attempt at this paper is two-way theory. Now, you may think that two-way theory is a strange place to want to look if you're interested in 3+1 dimensional field theories, because two-way theory has no 3+1 dimensional branes. There are 2 branes and 4 branes and 5 branes, but we're interested in a 3+1 dimensional field theory. So what's the deal? Why are we interested in two-way theory? But there is a second element, that we're interested in theories with only 8 rather than 16 supercharges. So we're not only interested in theories just on the branes themselves, just one kind of brane itself. We want somehow to break some of that supersymmetry. Now, something else that, I know there's so much to say, right? But something else that I've not told you about is the following. Though I think we may have gone through it in our string theory class. Is that when you put 2 kinds of branes together, you always break more supersymmetry than either one kind of brane or the other. But you can sometimes get away with not breaking all supersymmetry. The general rule with D branes is that if you have D branes with 4 directions not in common, then you preserve half of the supersymmetries of either one. So if you have, for instance, 0 branes plus 4 branes, that combination preserves 1/4 of 32, so 8 supercharges. Okay, 0 branes plus 4 branes does that. Okay, or if you have -1 branes and 3 branes, that does that. And there are other things one can do. The 0 branes and 4 branes, by the way, is a famous story. It enters in black hole counting.
What is it, -1 brane?
It's a D instanton. It's a configuration in a Euclidean path integral, not an object. Okay, but often a very important configuration because it generates terms and superpotentials that you would not otherwise. So it's a technical object, not a physical object, but a very important thing. Okay. So the rule is a bit different. Okay, the rule is a bit different when you have NS5 branes. Okay, and when you go through the supersymmetry analysis, turns out, okay, that the following configurations of D4 branes and NS5 branes are supersymmetric. When you have a D4 brane ending on an NS5 brane, I'm going to explain this in more detail. Okay, so let me give you a configuration that is supersymmetric. I may try to sketch a short argument that it's supersymmetric. Supersymmetric, but supersymmetric preserving 8 supercharges. Okay. So, consider the dimensions of space-time. Let's say space-time dimensions run 0, 1, 2, 3, then 4, 7, 8, 9 will plane over 1. Okay. And that's 5 and 6. D4 and NS5. Okay. Now in this table, wherever I put a cross, those directions are in the world volume of that corresponding object. Okay? And when I don't put a cross, they're not there. So 7, 8, 9 are transfers to everything up there. Okay? So no crosses here. My D4 brane extends in time, so everything extends in time, and in directions 1, 2, 3, but also in the direction 4. Okay? My NS5 branes extend in time in the directions 1, 2, 3, but they have to extend in 2 more spatial directions. Okay? And these spatial directions are 5 and 6. Okay? The intersection is, the spatial intersection is 3-dimensional. The world volume intersection is 4-dimensional. Okay? And that is what is going to be at the heart of getting a 4-dimensional field theory. Okay? So these guys intersect on a 4-dimensional world volume. Okay. Now, how am I thinking of this? The dimensions in which all of them are extended, we're not going to keep track of. They're there. The dimensions in which none of them are extended, we're not going to keep track of. They're also there. But these other 3 dimensions we'll keep track of.
Which is like a plane.
Exactly. So you imagine that there is a plane, this guy is the NS5. And is extended in a plane. And it's a line coming like this. It ends at one point on the plane, exactly. Okay? Such a configuration, turns out to preserve of the supercharges of your theory. Okay? How and why?
So 1/8 of 32.
Sorry, 8. 1/4. 1/4 of 32. So 8 supercharges. Exactly what we want for n equals 2 theories. Okay? Now, the kind of configuration people actually, if you have one of these guys doing it, and you put a few more, exactly parallel, the supersymmetry that you preserve depends on your angle. So if you put one and something else, that might break all supersymmetries. But you put more D branes exactly parallel, doesn't change the supersymmetry analysis. Or you put more 5 branes like this. Okay? And in order to obtain the n equals 2 theory that we studied before, Witten is going to look at this configuration. He's going to look at 2 NS5 branes joined by 2 D4 branes. Okay. Now what is the idea? The idea goes as follows. I will tell you this in much more detail.
The NS5 branes are also parallel.
The NS5 branes are parallel to each other, and the D3 branes are parallel to each other. Okay? Or both D3 branes obey, or D4 branes obey this. Both NS5 branes obey this. Okay?
So when you have a line in a 3-dimensional thing, there's much more than parallel, right?
Yes. There's much more than parallel.
Because they cannot be on the same plane.
But you want to look at configurations that are supersymmetric.
Like which one of those? They should lie in the same plane as well.
No, they have to have exactly the same. They can be here and here, that's fine.
What if?
But they have to be parallel. If you do this, that breaks supersymmetry. It could break it to all. You'd have to analyze. It could completely break it. You'd have to analyze. There are some things which will preserve some. And actually people have studied n equals 1 theories that way. There are some things that, I think the things that preserve some are twisting the n5 branes. in some orthogonal direction. I would have to check that. But generically, if you just make a generic move, it will just break all supersymmetries.
But this configuration will preserve 8 supersymmetries.
This configuration preserves 8 supersymmetries. Okay? Now, what can we say about the low energy? What can we say about the low energy dynamics? What can we say about the low energy dynamics of this theory? Louder, louder. Why do we require two NS5 branes? You will see. You will see from what I say immediately. The reason is that if you had one, we don't want anything to. The thing where you. Well, let me write down a formula and you'll see. What can you say about the effective dynamics of the four branes? So the four branes is described by some four-dimensional field theory, n equals 4. Yang-Mills theory, with G squared Yang-Mills equals 1 over, what was it? Square root alpha prime times G. Or did it go the other way around? Sorry. It went P equals 4. It's correct. Okay, excellent. Oh, but I got the other way around. Yeah. Yeah, no 1 by. What was making me uncomfortable was that I know that this theory should become strongly coupled at high energies. Alpha prime E is the square root alpha prime E is the dimensionless parameter. Yeah. Okay. So it has this G squared Yang-Mills. Now, because this thing is compactified, suppose we got this thing of length L. We look at long distances compared to this compactification length. Let's call this length whatever it is. Let's call it L. Then the effective G squared Yang-Mills, the action will pick up an L by G squared Yang-Mills. So the effective G squared Yang-Mills 3 will be equal to G squared Yang-Mills 4 divided by L. Okay? So we've got G squared Yang-Mills 3 is equal to square root alpha prime by L and G. In 0, 1, 2, 3. 0, 1, 2, 3. 0, 1, 2, 3. That's where G3 Yang-Mills lies. 0, 1, 2, 3. 3 meaning G squared, 3 plus 1 dimensional. 3 brane. As a G4 Yang-Mills lies in 0, 1, 2, 3, 4. 4 is this L dimension. Right. I'm sorry, the notation's confusing. Okay? So, what we want to do is to take some low energy limit. So we get a field here. Okay? We want to take some low energy limit, so we get a field theory. But our low energy limit should be such that this G squared Yang-Mills 3 is not forced to either 0 or infinity. Some value, so that we can study field theory at finite coupling. Okay? So, we can do that in many ways. Okay? But one way we could do that, for instance, would be to take alpha prime to 0 and to take L to 0 with their ratio fixed. The alpha prime to 0 ensures that closed strings are decoupling. Because then Newton's constant is going to 0. Okay? So it ensures that closed strings are decoupling. And this is one way to take the limit. I will tell you a little bit more about this limit in a bit. Okay? So, We will study precisely the limit we want to take in a little more detail next lesson. But roughly this is the idea. This, Sunil, is why we wanted to keep L finite. If this was infinity, G squared diagonals here would just be 0. We don't want that. Okay? And the idea here is now to try to study what happens in this brane configuration and see if we can recover the Seiberg-Witten solution. Now you might think, look, how are you going to recover Seiberg-Witten? Seiberg-Witten was complicated quantum field theory, symmetry analysis, anomaly analysis, monodromy analysis, curves. How are these pictures going to reproduce something so interesting? And the basic idea is now to go to M theory. Okay? Remember that a D4 brane, if we add the circle direction, then a D4 brane was an M5 brane on a circle. So in M theory, both the objects that appear in this picture become the same object. Because an NS5 brane was an M5 brane in the transverse directions. Whereas a D4 brane was an M5 brane including wrapping the circle. Okay. Now, we can add the M theory circle and do a more serious analysis of this problem. The more serious analysis, which, as we will see in more detail, but the more serious analysis is this. Now the question is becoming this. I have a configuration of an M5 brane that is going to wrap dimensions 0, 1, 2, 3. That, of course. But 2 more directions. And I have to do it in a way that preserves 2 supersymmetries. 8 supersymmetries. Now, you see, this was a pretty singular looking configuration from the point of view of string theory. Something ending on something else. On the other hand, from the point of view of M theory, this ending has become a tube. This was a plane. What you should get is some sort of smooth curve. I will explain to you next time that curve is the Seiberg-Witten curve. The curve we found in the solution of the Seiberg-Witten equation is the curve on which these branes live. That is the connection. Okay, we will see that next class. We'll have to do a little more preparation. Questions, comments about the general? Curve is this misnomer that mathematicians love. Right? If they have one complex function and 2 complex variables, they call it a curve. Suppose I have an x and y, 2 complex dimension space, and I have one analytic equation. They call it a curve just because if we had 2 real directions and we had one equation, we would call it a curve. It's a plane, okay, but they call it a curve.
Sorry. Is that x function of y which
Though, exactly. This curve, this thing that we wrote down, x minus 1 to x plus 1 and x plus u, x minus u. This, in some version, we will get out of the description of this brane. So this thing that somehow came through a lot of complicated field theory will just come staring at us out of geometry.
Why is this smooth?
Why is this smooth? You see, in M theory, both the 4 brane and the NS5 brane were an M5 brane. Both were 5-dimensional objects. Now, the thing that was not smooth in string theory was that you had a 4-dimension, like you had a line ending on a plane. That can never happen smoothly. But suppose you had a tube ending on a plane. That can happen like funnel, right?
For that specific, then it can still end as a...
It can, but then now you have to work out the condition of supersymmetry.
Supersymmetry. That will make it...
That will be. In fact, let me tell you, the condition of supersymmetry, the condition that this a general condition that the M5 brane preserve its supercharges in such a configuration is that the M5 brane is described by a holomorphic curve. Clearly this will not be holomorphic.
But here, to preserve them, you need to have this.
You need to have this, and this is the fact that the smoothing out will happen on a scale which in the limit G string goes to 0, will go to 0. So it will look like, okay, but if you look at the real description, it's always smooth. And that description will, in fact, let me give you one idea of the picture and then we'll stop. You see, this is an infinite plane. You can think of that like the U-plane, roughly. Remember, we had a double-sheeted cover of the U-plane. That's why there are two NS variables. Okay? Remember, we had two cuts going between them. And you remember our picture was that the first cut and the second cut, this one is a tube. That tube will be this tube. And the second tube will be this tube. So you'll actually physically see the tubes going between the two spheres. Okay, excellent. We'll continue this next class.